Before we start
our second example, I wanted to just remind you of what we've done before when we dealt with vectors. We talked about vectors using the algebraic notation where we can say, okay, vector V has the components 3 and 4. Okay, and if we wanted to know the magnitude of the vector V, probably shouldn't have used V. Let me use U because we're using V to mean velocity. I don't want you to get confused there. So vector U is the vector 3, 4. That means if you start at 0, you go over 3 and you go up 1, 2, 3, 4. Or if you start anywhere, you go over to the right 3 and you go up 4. And the tail of the vector is at the beginning and the tip of the vector is at the end at the coordinates, let's say 3, 4. And if you wanted to know the velocity, the magnitude of this vector, you could use the Pythagorean theorem. Would be 3 squared plus 4 squared, or you could recognize this is a right triangle, and we know that we have a 3, 4, 5 Pythagorean triple, so we know that the magnitude of vector u is 5. Okay. Well, the cool thing is that all this new notation that you're learning works exactly the same. The same rules apply. So let's take a look. We have a particle moving in the xy plane. Again, it could be all over the place. So that at any time t is greater than or equal to 0, the position is given by these two parametric equations. What we want to find is the magnitude of the velocity vector at the time t equals 1. Okay, so let's take a look. Let's actually write out the velocity vector down here. The velocity vector is the vector, the derivative of the position, the x position, or the position in the x direction with respect to t, followed by the derivative of the y position with respect to t. Okay, and that is equal to the derivative of t squared plus 3t is 2t plus 3, comma, the derivative of the y component would be 3t squared minus 6t. So this is our velocity vector. So we have our, if we want to look at this in terms of let's say a right triangle. So, okay, we have our x component, our dx dt, is our change in the x direction, and we have our dy dt is the change in the y direction, the rate of change in the y direction. Okay? The rate at which y is changing with respect to x. And let me use a different color for my velocity vector. So the velocity vector is right here. That's the velocity vector. Okay? And we want to know the length of that. Well, if we want to know the length of that vector, which is what it says find the magnitude of the velocity vector. So we want to find the length of the velocity vector, and that's equal to the square root of dx dt squared, so x prime of t squared. I should have probably written it as dx dt squared, but I don't want you to get bogged down with the notation. I want you to understand conceptually what is going on. So this is equal to x prime of t, but I don't want that to confuse you. This is y prime of t. I just don't like to write the fractions underneath the radicals. So I have y prime of t squared. So I'm just using the Pythagorean theorem. That's what it says. The magnitude or length of the velocity vector can be found by using the Pythagorean theorem. Since the horizontal and vertical components make a right triangle, with the vector itself as the hypotenuse. Therefore, its length is given by this. Okay. Well, we have x prime of t. We know this is our x prime of t, right? Okay. And x prime of t is 2t plus 3 squared. And our y prime of t is 3t squared minus 6t. It looks like it's going to get really, really messy. However, don't forget, we're trying to find the magnitude of this velocity vector, which was what we did, but at the when t is equal to 1. So this guy, the magnitude of the velocity vector at the time when t is equal to 1 would equal, let's put a 1 in for t, and we have 2 times 1 is 2, 2 plus 3 is 5, 5 squared is 25. A 1 in place of this t over here would be 3 minus 6, negative 3, quantity squared, so negative 3 quantity squared is 9. And we have the square root of 25 plus 9, which is the square root of 34. So that's the length. Let's look back, make sure we don't have to find anything else. We wanted to find the magnitude of the velocity vector when t equals 1, and we did just that. We found exactly what we were looking for. Okay. So that's the length of the velocity vector, the magnitude of the velocity vector. One thing that I wanted to point out, I kept this in your notes here, is that the formula for the magnitude of the velocity vector, I'm running out of room there. The formula for the magnitude of the velocity vector is the same as the formula for the speed of the vector. And why is that? The formula for the length of the velocity vector is the same as the speed of the vector, which makes sense because the speed is the magnitude of the velocity. So it's the same stuff you learned way back when. Speed is the magnitude of velocity. It remains the same concept even when we're dealing with vector-valued functions. So that is really cool. And where's my other piece of paper? Here it is. Final example. A particle moves in the xy plane so that we have our x and our y coordinates of any point in the xy plane based on these. Why did I grab that? Based on these parametric equations. Now keep in mind, t ranges from 0 to 2 pi, and it says the path of the particle intersects the x-axis twice. Okay, so the path of the particle intersects the x-axis at the points where the y component is equal to 0. So if you think about it, you've got this particle, let me see here, you've got this particle moving around, and we don't know where it starts, but all we know is that it hits the x-axis once, and it keeps going, and then it hits the x-axis again, and it keeps going, and maybe it stops in the same place that it started. It doesn't really matter, I guess it would, because it's 0 to 2 pi, and then we repeat. So it starts somewhere, but it hits the x-axis twice. Okay, write an expression that represents the distance traveled by the particle between the two x-intercepts. So let's say we have to pick a starting point here. We have a starting point here, and let's say it goes this way. It doesn't really matter whether it goes, what way it goes. We know that it hits here at some point, so we know that that's our A, and then it keeps going. Okay, and then here's our b. We got to figure out what that a and what the a and the b are, but what we do know is again that that the path of the particle after it hits here, or when it hits there, it's where the y component, this guy, is equal to 0. So a and b, it's when the y component of the vector is equal to 0. So all we have to do is solve this equation setting y equal to 0. So in other words, when 0 is equal to 1 minus the sine of 2 sine t. And why is that? Because x and y are the positions of, x and y are the coordinates of the points around the curve based on whatever time t. Okay, well, the y position at a point where the curve crosses the x-axis, the y position is 0. Okay, so when the y is 0, it has no height. Okay, so it's on the x-axis. And solving this equation by adding 2 sine t to both sides, we have 2 sine t is equal to 1. We have the sine of t is equal to 1/2. So now it comes back to, again, knowing your unit circle. Where is the sine of t equal to 1/2? Well, it can't be here or here, because remember, all students take calculus. All the trig functions are positive in the first quadrant. Only the sine is positive in the second quadrant. And specifically, where is the sine equal to 1/2? Well, that's at pi over 6 and at 5 pi over 6. Okay? So here, look at this. We've got starting here, so we start here, and we go this way, because it says we go from 0 to 2 pi. So we go this way, and we're going to hit pi over 6 first, keep going, keep going, keep going. We're going to hit 5 pi over 6 next. So the a then would be, therefore, a is pi over 6. Okay, that's our a. Remember, we hit a first, and then b would be the 5 pi over 6. So we've got our a and we've got our b. Well, how do we find the distance traveled? Well, distance traveled is the integral of the speed. The integral of the speed, so distance traveled would be the integral from a to b of the speed. We always integrate speed if we want to find distance traveled. Okay. Well, that would be the integral from pi over 6 to 5 pi over 6. And the speed would be absolute value of the velocity, right? We don't have that yet. Okay, so let's do that. Let's find the absolute value of velocity, or the length of the velocity vector. Okay, well, where are we going to do that? Let's do that where we can see. Let's do that right up here. Okay, let's find the velocity vector. The velocity vector, first of all, is the x prime, y prime, which is, so x prime would be positive 4 times the sine of t. So the derivative of, I knew that was going to happen. The derivative of radical 3 minus 4 cosine t is 4 sine t, and the derivative of 1 minus 2 sine t would be negative 2 cosine t. Be really careful. There's a lot of places to make mistakes. So that's the velocity vector, and the magnitude of the velocity vector then, can I get that all on the same slide? Yeah, okay. So the magnitude of the velocity vector, keep our integral, is the square root of